Alright, Assalamu alaikum. So today I'm going to give you examples of electromagnetic induction. And I would like to start off with a demonstration. That demonstration involves the effect that is called magnetic braking. So here what we have is, this is an electromagnet, which means that there is a solenoid here in this frame and there is a solenoid here, and this is a U-shaped piece of ferromagnetic material such as soft iron, which has a high permeability. We've already seen our recitations and tutorials on magnetic materials. So when a current passes through these coils, a flux is produced, and the coils are bound in a direction such that the flux is produced, say, from left to right or from right to left. So the coils are bound in opposite sense in these frames. So suppose the coil is bound like this. If the current flows like this, then a magnetic field will be produced from left to right. The coil here would also be wound in a similar direction, because that would make the field go from left to right. So these are two coils that are bound in the same direction, in the same sense, and they produce a magnetic field. So the magnetic field lines start here. They don't in fact start everywhere. We can consider that in our path that these magnetic fields come from here. This is a soft iron piece. This is a tapered piece, so the field lines are concentrated and they go from left to right. They have to pass through air. They can't stop anywhere because of Gauss's law of magnetism. They have to be continuous. So the field lines circulate in this direction. They enter this tapered pole piece, which is a soft iron piece. Then they go around into this frame and they make a complete loop. So like all magnetic field lines, the magnetic field here is also in a closed circuit. You cannot have field lines that terminate somewhere or originate somewhere, because you can't have magnetic monopoles. So if you take any closed surface area, for example, you draw a cube here, the field lines coming into the cube will be equal to the field lines going out of the cube. So this electromagnet produces a strong magnetic field. You can go up to 1 Tesla as in this particular electromagnet. You pass current through the coils, it produces a field. But the coils also heat up. So if you produce large fields, you need to cool this electromagnet. So that's why you have connections from where you can pass in water and circulate water through these coils so that it radiates off its heat. Now what I have here is a current source. This current can drive current through the electromagnet, and when it drives current, a magnetic field is produced. So now the direction of the magnetic field, say, is from left to right. Now at the same time, inside this electromagnet, I have a pendulum. But the pendulum is made up of a metallic disc. This is a side view of that metallic disc. It's a circular disc and it's metal, it's made of aluminum. So what I could do is, I could actually oscillate this disc between the pieces of, the pole pieces of the electromagnet. So this magnet oscillates, this metal oscillates just like an ordinary pendulum. It has a moment of inertia, it shows circular motion. So far so good. Nothing special about it. Now what I would like to do is, I would like to switch on the current so that this coil is energized and it produces a magnetic field, and that magnetic field, say, goes from left to right. And I would like to see what the effect is on the oscillatory motion of this magnetic pendulum, So let me restart this oscillation. Now it's going to damp off with a natural rate because of air resistance, and it's going to sustain its oscillations for a long duration of time. Let me start the oscillations again. Now I'm on the electromagnet. So it's a small current, 0.2 amperes. I ramp up the current and it comes to a sudden halt. Just passing a current through this electromagnet makes this pendulum come to a sudden halt. Its motion is arrested all of a sudden. So let me repeat this experiment. This very little current that goes through this electromagnet is about 0.2 amperes. I restart the oscillator, I restart the oscillations, I ramp up the voltage, and this pendulum comes to a sudden halt. So I haven't applied mechanical brakes, I don't have a hydraulic arrangement that arrests the motion of this pendulum, I'm just applying a magnetic field. So this phenomenon is called magnetic braking. Now could anyone come up with a succinct, brief, concise, accurate description of why this phenomenon occurs? What is the underlying mechanism? G. Usmanini. Can you speak up, please?
The pendulum passes between the electromagnets, it cuts magnetic flux at the pole. So that will eddy currents inside the conducting pendulum. Those eddy currents produce a magnetic field that opposes magnetic field experiences. So that's why.
But it can't oppose this external magnetic field will exist because the current is passing through this electromagnet. It can't oppose the external field. So the best it can do is it can avoid the external field. So if this pendulum is outside the pole pieces, it sees zero flux. So it would like to keep the flux through the material zero. So the only way it could do that is that it would like to avoid passing through the pole pieces, which means it would not like the flux to change. And if it would not like the flux to change, the only way it could do is either it can remain out of the pole pieces so that the flux through it is zero, but that's not gravitationally energetically favorable because the potential energy is high. So it would rather like to come to a sudden arrest in between the pole pieces so that the flux, whatever flux it is, through the metal disc remains constant. You cannot avoid constant fluxes, you don't want fluxes to change. So this phenomenon of Faraday's law or electromagnetic induction causes eddy currents inside, circulating currents inside this disc. Now if this magnetic field is pointing from left to right, what would be the direction of these eddy currents? They would point. So the eddy currents would produce a field that opposes this field. So the field would be pointing from right to left, which means that the eddy currents would be circular. They would loop around into the plane of the blackboard and come out. So they will be like a spiral, going in, coming out, like this. Okay? So these eddy currents will produce a flux that opposes the externally applied changing flux. Let me repeat this experiment once more for the newcomers. So I've set this pendulum into oscillation here. And I ramp up a current. This pendulum comes to a sudden halt. Okay, once more. So this is the phenomenon of magnetic braking, and it results out of eddy currents. Those eddy currents are produced because of electromagnetic induction. There is a non-conservative electric field that is set up inside this disc, And if I look at this disk from the front, the eddy currents are circulating, say, in this direction, because a non-conservative electric field has been set up in this direction. It's a curly electric field, and it's non-conservative or non-coulombic. It's not arising out of charges. This metal disc has no charges on it. There's no distribution of charges on this metal disc. It's a neutral body, but still it can sustain an electric field. That electric field is originating because this disc is piercing a magnetic field that is changing with time. And that magnetic field, say, is pointing into the plane of the blackboard. So eddy currents are produced so that the flux or the magnetic field due to those eddy currents are pointing out. And it's a conductor, so this non-conservative electric field, no doubt it's an electric field nevertheless, can produce a current. Because whenever you have an electric field, it produces a current density. Now this electric field could be coulombic, non-coulombic, it doesn't matter. Once the field has been set up, it's immaterial what's the origin of the field. If it's a conducting material with a high conductivity, it can produce currents, which in this case are called eddy currents. Alright, now what if I use, instead of a solid disk, I use a disk of this kind? Alright, now this disk is variegated, or it has these corrugations, or it has these incisions into it, so that if eddy currents are made to pass, these eddy currents encounter insulating barriers of air. So the conductivity of this medium, or the resistance of this medium, is higher. The conduction, or the inverse of the resistance, is smaller. The resistance is high, the eddy currents will not be able to produce a strong enough opposing flux. So eddy currents are being arrested in this medium. So the damping will be less significant. So let's try that out. But to give you an idea of that, let's repeat this once more so that you get an idea of the amount of time it takes for this magnet to come to a certain halt. So I start the oscillations. And I ramp up the current to 1.8 or 1 amperes. It just comes to a sudden stop. Alright, just suddenly. Now I would like to take off this pendulum and replace it with the other disc. Alright, so now I have another kind of disk in which eddy currents will no doubt be produced, but this disk has been variegated, which means that in the lower semicircle, the lower hemisphere, it has these incisions. So eddy currents may only flow through a closed path. They have to flow through closed paths. They can only pass inside this region. So this will be the direction of the eddy currents. They cannot go through the entire region, so the amount of flux that these eddy currents produce is going to be smaller. So the effect of magnetic braking should be less pronounced. It would still be there, but it's going to be less pronounced. Let's see that. Let's set this into oscillations first. Okay, now ramp up the current. It's gone to 1.9 and it's still oscillating. Okay, so in the previous case at about 1.7 or 8 amperes, the eddy currents were so pronounced that magnetic braking was playing an important role. Now, eddy currents no doubt exist, but they are of a much smaller magnitude because the conductivity of this medium has been interrupted. The resistance is higher. So the amount of eddy currents, or in amperes, is going to be smaller. The flux that they're going to produce that opposes the changing flux is going to be smaller. So braking is going to be less significant. Let's repeat this once more. So it's set into oscillations. Two amperes, and it's still oscillating. So braking has actually been arrested in this case. So this is all that I have to show as a practical demonstration in the class today. These eddy currents, by the way, Eddy was a scientist. In Europe, they are generally called, or especially in Italy, they're generally called Foucault currents, because Foucault independently discovered these currents or motivated these currents. Eddy was an American. So these eddy currents are produced because of Faraday's law, because of electromagnetic induction. Whenever there is a changing flux, there is a non-Coulombic electric field that is set up that can cause currents whenever you have a conducting medium. Now suppose you have a transformer. And I'm just drawing one arm of the transformer. So this is one arm of the transformer, and on top of this transformer you have a winding. Right? This is one coil of a transformer, say the primary coil. And whenever a current passes through this coil, if this current is changing with time, for example, if it's an AC current, which oscillates with time, of course, this solenoid, it's in effect like a solenoid, is going to produce a magnetic field. So if this is the direction of the sense of winding and this is the direction of the current, the field will be produced in the downward direction in the positive half cycle. In the negative half cycle, it's going to be produced in the opposite direction. So you have a flux that is circulating in the core yoke of this transformer, and the flux is constantly changing because this current is changing. The flux depends upon the current. Now whenever you have a changing flux through a medium, for example, this could be a conducting medium or a semi-conducting medium, a partially conducting medium like iron. Iron is conducting. Right? You need a soft material such as soft iron, but that's the downside, it's conducting. So a non-conservative electric field will be produced, and that field will cause eddy currents to circulate inside this material. Now if you look at the direction of those eddy currents, those currents would be pointing such that if in this duration of the AC cycle, if the external field is pointing down, the eddy currents will produce a field that's pointing up, which means that the currents will be circulating like this. So these currents will produce an upward field. Now you want to arrest these currents because these currents will actually cause resistive heating. This material no doubt has resistance. So whenever a current I flows through a resistive material, it produces a heating effect. And the amount of energy that it produces per unit time is I square R. And this transformer core heats up. So you don't want your transformer cores to heat up because that will degrade the quality of electricity that you receive. Transformer is going to heat up, and that will cause all kinds of problems. You don't want your transformer wires to melt, for example. These temperatures could be really high. So you make a lot of effort in cooling these transformers. You use special kinds of oil and you put a radiator with the transformer so that it dissipates its heat. This heat is being produced due to these eddy currents. So you would like to reduce the effect of these eddy currents. And how could you reduce the effect of these eddy currents? Instead of having a solid core, you make sheets of iron that are intercepted by insulating material, which are called laminations. So instead of having a solid core, you have a sheet of iron, and next to that sheet of iron, parallel to it, you have an insulating material, for example, mica. This is called a lamination. And then you have another sheet of soft iron. Then you have another lamination. So now eddy currents that are produced in a plane which is horizontal, they have to pass through this insulating material. So the eddy currents will be reduced. And when the eddy currents are reduced, I square R is going to be reduced. So the heating of the transformer can be kept under control. So eddy currents are really important when you're designing magnetic systems or systems that use electricity and magnetism together. In the previous lecture, we also saw a demonstration of Lenz's law. This is also Lenz's law. Lenz's law simply states that an EMF is induced or a current is induced, which is called an eddy current, which opposes the source, and the source is the changing magnetic flux. Alright, now let me move back to Faraday's law and look at different manifestations of Faraday's law. And what does this have to do with an EMF? So what is the induced EMF? Okay, यहाँ तक कुछ सवाल पूछना है? जी.
Can you explain the lamination current is the shock pattern?
If you look at this construction from the top, okay, from the top you have an iron piece. You're looking at this sheet from the top. Then you have an insulator, which is mica, for example. This is the lamination. Then you have another iron piece. Then you have a lamination. Okay? Compare this to the case of having a solid iron piece. Now in this particular case, eddy currents will produce and they can go all around this area. So they'll produce a large flux. In this case, you'll have small regions of production of eddy currents. They can't go through the insulating material. Suppose it's a very high resistance material. So you have these small loops or rivulets of eddy currents. Now see what's happening here. The current is passing in this direction in this region and it's passing in this direction in this region. So there's no flux here. So the amount of opposing flux that is produced is reduced because the eddy currents are smaller. The eddy currents are smaller, they will produce less resistive heating. So this is the basic principle of why lamination is done and why do transformers heat up in the first place. Another very interesting effect of eddy currents, before I move on to this manifestation of Faraday's law, is suppose you have a ferromagnetic material and this domain wall motion inside this ferromagnetic material. So I have a material in which there is a domain which has its moment pointing in one direction, and in a neighboring domain the moment is pointing in an opposite direction. We know that if we apply a field, say in some direction, this domain will grow at the expense of this. So domain wall motion takes place. Now suppose, so with time what's going to happen is that this domain is going to grow larger in size and this domain is going to shrink. So what really is happening is that this domain is progressing with time in space. It's moving, it's translating. Now when you stand underneath a high power transformer in your streets or on the road, you hear a humming noise. Where is that humming noise coming from? Why do transformers sound? Why do they make a sound? Why do they vibrate? Right? Electricity shouldn't give you a sound. So what's happening here is that no material is perfect. What we have is an impurity inside the medium. Suppose you have a domain wall that comes in contact with an impurity, an inclusion inside the medium. No material can be made perfectly pure. So there's an impurity here. So now look at this impurity. Let me zoom in a little bit on the impurity. In this region, in this domain, the field is pointing in one direction, and here the field is pointing in the opposite direction. And this domain would like to move towards the right. But it has hit upon an impurity, an inclusion. Now what this magnetic field, this B inside the medium is going to do is that this medium is going to be magnetized. So if it will make a south pole here, a north pole here, and it will make a south pole here and a north pole here. So this magnetization inside this impurity is going to create a mini magnet inside this material. Now these magnetizations are pointing in opposite directions inside this impurity. So the magnetization of this region, the total magnetization of this region is going to be 0. And this, as you know, that this is favorable as compared to this configuration, in which this impurity is solely and wholly inside this domain. If this impurity is solely and wholly inside the left domain, it will have a magnetization pointing in this direction. So which of these configurations, or this and this, how do you compare the energies of these configurations? Of course this has smaller energy, because it doesn't have a magnetostatic component. It has no flux leakage. So this is a smaller energy configuration. So the domain would not, if it intercepts an impurity, it would not like to move forward, because if it does move forward, then this impurity will solely and wholly lie within one domain, and it will cause the energy to go up. So the domain wants to move, but the impurities are holding back the domain propagation. Okay? So what's going to happen is that if you look at the MH curve, this is H, this is M. And this is the kind of curve that you obtain. But if you look really closely, if you zoom in here, this curve is actually made up of a staircase-like arrangement. So the H goes up, but the magnetization remains constant. Look at the steps of this stair, the levels of this staircase. H is going up, but the magnetization is not going up, which means that the domain wall is unable to move, even though you are increasing the applied field, because the domain wall does not like to leave it's in some kind of relationship with the impurity. It does not like to move on. It likes to remain pinned to the impurity. The domain wall is pinned to the impurity. It's latched on to the impurity because that gives you a low energy configuration. So what's going to happen is that even though you're increasing the H field, the magnetization is not going up, because it's just that this domain wall is locked. But it cannot hold on. The effect of the external applied H is so large that finally this domain wall snaps. It just moves on all of a sudden, and it moves on in jerks. It's just that the impurity has given up in holding on to the domain wall. And when it jerks, there is a sudden motion. That sudden motion causes vibration, and it causes sound. Alright? And why is that? Why is there a sudden motion? Because the magnetization changes suddenly. You see, here, if I zoom in on this a little bit more, H is increasing but magnetization is steady because the domain wall has been pinched to an impurity. All of a sudden, this impurity just gives up. It can no longer hold on to the domain. The domain wall has to move on because the energy of the overall system has to be lowered because of this applied field. So, जिस तरह आप एक पहाड़ से आप गिर रहे हैं और आपने हाथ पकड़ा हुआ है और आखिरी आरज़ू है कि आप हाथ छोड़ें ना, लेकिन अचानक जब आपकी हिम्मत जवाब दे आप हाथ छोड़ देंगे. So the domain wall just moves on because it is being dictated by this externally applied field. The impurities are playing their minor role and they can arrest the motion of the domains only to an extent. Suddenly, the magnetization just goes up in response to this H and the domain wall moves on. So if I make a diagrammatic representation of this, there is an impurity, the domain wall is here, so everything is fine. Then we have the domain wall that's progressing to the right. It gets onto this impurity. Then what we have is that the domain wall tries to move on, but the impurity is hinging it back. So it just remains latched at the position of this impurity. Suddenly, if this field is so large, the external field is so large, this domain slightly snaps off. It just moves on. The impurity cannot hold it back. And when it does that, there is a sudden change in the magnetization. And all materials have a property which is called magnetostriction. Magnetostriction means that you apply a magnetic field, the object expands, physically it expands or contracts. Okay? You apply a field, an object will physically expand. A piezoelectric material is a material in which you apply an electric field, the object may expand or contract. If an object expands or contracts, it can develop an electric field. That's what a piezoelectric material is. And that's what buzzers are made of. You apply voltage to a buzzer, it expands and contracts and gives you sound waves. That's how a buzzer works. It's a piezoelectric material, but all materials have a magnetostrictive property as well, which means you apply a magnetic field, or when the magnetization changes, the object expands or contracts. So here, when the magnetization suddenly changes, there's a delta M. The object suddenly expands or contracts, depending upon the material. And when it suddenly expands or contracts, there is oil that is circulating around the core of a transformer. It experiences a pressure. And when the entire big power transformer is breathing, because it's physically expanding or contracting, it will produce sound waves. It's going to affect the pressure of the sound air around it. That's going to produce a humming sound. That's why transformers are always noisy, especially the high power transformers, or especially the high frequency transformers. Okay? The other property that's going to take place is whenever there's a sudden change in magnetization, which means that the field inside the material is going to change, because the field inside the medium is mu naught H plus M. Now if this M is suddenly changing, there is a sudden change in B. A sudden change in B will produce an eddy current. It will produce an induced EMF. And eddy currents will start flowing, and they will cause heating of this object, of this transformer. So no transformer has 100% efficiency. Some of the energy is lost into sound, and most of the energy is lost into heat, thermal energy, because of eddy currents. This phenomenon, that this hysteresis loop is actually comprised of these small steps. And I can actually show you a demonstration that you can hear this effect. This is called the Barkhausen effect. Named after the discoverer of this effect. Okay, I give you half a minute. I'll answer the questions and then we'll move. Yes, what's your question? डोमेन, इस डोमेन में और इस डोमेन में उस पे मैंने भी कोई डायरेक्शन नहीं दिखाई. ये इम्प्योरिटी है, इम्प्योरिटी का एक इंक्लूजन है. हाँ, उसके अंदर दो डोमेन्स बन गए. जी जी, चलिए थोड़ा सा आगे चलें थे, शायद आपको सवाल का जवाब मिल जाए. अच्छा सवाल पूछना आधा इल्म होता है. अच्छा, I would like to talk about different manifestations of Faraday's law. Now, we've already noticed that if I have a region in which the flux is changing, for example, the field is pointing out of the plane and only inside this region which I've drawn as a circle. This is the field. And this field is increasing with time. This is given to you. That dB over d out, dt is outwards and increasing. So if I take some point P outside this region, what's the magnetic field at point P? Zero. There's no field here. There's no electric field here per se. If this field were not changing, there were no electric field here. The old version of Faraday's law, which we discussed before we were talking about conservative field, states that E dot dl about a closed path has to be zero. But only this field is constant with time. If the field is constant with time, this no longer holds true. This zero has to be replaced by something else. And we've learned that this has to be replaced by minus dB by dt of, that is the derivative of the flux, magnetic flux, that is through an area which is inside some path. Now, if I would like to calculate the electric field here, and if I would like to use one of Maxwell's equations, I really need a line integral. So I need to choose a path. So if this is a symmetric situation, this is circular, the best choice, in fact the only choice of the path that would make any sense is a circle. So around this path, if I take point P, if I take point P dash, if I take point P double dash, it doesn't matter because all of these points are equivalent, everything is circular. So the electric field here is going to be the same as the electric field here if it existed. Now this electric field has nothing to do with charges. There are no charges in this system. So it's a non-Coulombic field or a non-conservative field. Why non-conservative? I'll let you know in a minute. And the line integral of this field is going to be given by this. Now which area are you integrating over? This area is the area which is inside this path, this dashed path that I've drawn, all of this area. What's the flux through this entire area? Now there is no flux through this region, there is no flux here because there is no field here. The only flux that exists is inside this circle. So you just have to integrate over this area and then you differentiate with respect to time. So if this flux is pointing out, because the field is pointing out, the area is pointing out, this and if this field is changing with time, and if I take the integral, this will become minus a dB by dt. Alright? Because locally, everywhere, the field is pointing out and the area is also pointing out. Locally, the dot product is just unity, the angle is 0. So I can just take the local dot product, the angle is 0, which means that I can integrate dA separately, bring it out, and I get this relationship. Now this electric field will have a direction, and it's going to be a curly electric field. Now, Lenz's law will determine the direction of this electric field. Now, if the field is outwards and increasing with time, okay, field is outwards, it's increasing with time. So, the change in field is outwards. So, the electric field, the non-conservative field, the non-Coulombic field will be produced in a direction so that it opposes this effect. So, if we were to place a charge here, some hypothetical test charge here, a positive test charge here, then that charge should move in such a way under the action of this non-conservative field so that the field that this moving charge produces is going to be opposing the change. Now the change is outward, so the current or this hypothetical charge has to move under the action of this non-conservative field. Of course, there's going to be a force on this charge, which will cause the charge to move. So the charge will move in a direction such that it opposes the change. The change is outward. The field that this moving charge should be inward. So which means that this charge has to move in a clockwise fashion. Which really means that the electric field, the non-Coulombic field, is going to point like this. It's going to be tangential to the circle. Okay, so this gives us the proper direction of the electric field. And the round trip integral of this non-Coulombic field is not 0. So if you place a charge here, it's going to accelerate. It's moving in a circle, so it's always accelerating. Because there's centripetal acceleration always. Okay? It's going to move around in a circle. Its speed will not increase because of the centripetal acceleration. The speed is going to remain constant. So the kinetic energy is not going to change, by the way. Anyway, a curly electric field can exist. If I replace this scenario with a scenario in which I have a changing field, now the path that I take is different. Suppose I take this path. So the arrow shows the direction which I move around the path. It doesn't show the direction of the electric field. If I take this path and I calculate E non-Coulombic dotted with dl around this path that I've chosen, let's call this path P. What is the right hand side going to be equal to? 0? Yes, it's going to be 0 because through the area on whose outer perimeter does this path lie, there is no changing field. There is no changing flux. Remember, field can change because of flux or because of area. So this is 0. But that does not at all mean that the field here is 0. The electric field here will still exist because of this changing field. And it's going to be, if I draw a hypothetical circle here, it's going to point tangentially to the circle here. So the field might exist everywhere. It might even exist here. It will exist everywhere inside this region. But that does not mean that the line integral of the field will not be 0. The line integral will be 0. So the line integral being 0 means this is a global property. This summation is done over an entire loop. But that does not mean that the electric field everywhere is 0. Remember that. We've seen this kind of argument in Gauss's law as well. So the electric field's line integral over this loop is going to be 0. But that does not mean that the electric field is going to be 0. Okay, now let's look at a very interesting discussion. This E dot dl has dimensions of voltage, potential. When we were looking at circuits, we drew a battery. This is a model of a battery, and the two terminals of the battery are joined by a wire. Suppose this is the positive terminal of a battery. This is the negative terminal of a battery. Now what is happening here is an electric field is set up inside the wire because of negative feedback. Initially because of the dipolar field of the battery, but then because of negative feedback. We've seen how an electric field is set up inside the wire. That causes a current to flow through the wire. Now what's the direction of the electric field inside the wire? It's going to curl around. The electric field, this is the direction of the electric field inside the wire. Okay, axial with the conductor. This is E inside the wire. But what's the direction of the electric field inside the battery? It's going to, of course, it's going to point from the positive terminal to the negative terminal. It's opposite to the direction of the field inside the wire. It seems as if this electric field is just in the wrong direction inside the battery. This is E inside the wire. Okay? Now if you take a round trip through this circuit, for example, you start at point A, move to point B, C, D, and back to A. You're making a round trip around the circuit, and then you take E dotted with dl around the round trip, the closed path. So what is this round trip integral going to be equal to? 0. Because all of these electric fields have been set up by real charges, Coulombic charges. Electric fields are set up by the battery. The electric fields on this wire are set up by the surface charges, right? By surface charges. So all of these electric fields are set up by surface charges. So the round trip of this electric field, which is a Coulombic field, is 0. Now if I twist and turn this circuit in any way that I choose, for example, we've seen circuits of this kind, which I have a battery, and I have drawn circuits of this kind as well, to show you how surface charges are developed. In this round trip, if I make a round trip in this case, okay, I go around this circuit, I've changed the path, but still E dot dl is going to hold. So the round trip of, on any surface, if I make a round trip, the line integral of a Coulombic electric field is going to be 0. So such a field is called a conservative field. Which is path independent. However, this electric field, its line integral does depend upon the path that you take, whether it encloses a changing flux or not. So this electric field that is produced due to time varying magnetic fields is indeed non-conservative. Okay? The other point I would like to make is quite interesting. In this particular case of a conservative electric field, I can define the EMF of a battery. EMF, and I denote this by E. Inside this battery, what's happening is I can model this battery as a conveyor belt that is being operated by a pulley, and the conveyor belt is shifting. It's taking positive charge, okay? It's taking a positive charge from the positive terminal and it's taking a negative charge from the positive terminal and depositing it onto an already negative plate. Look at the direction of motion of the electrons. If this is the direction of the electric field, the drift velocity of the electrons is in this direction. This is the drift velocity of the electrons. So the electrons are moving around the circuit from the negative plate to the positive plate. Inside the battery, they must move in the same direction. So this is the direction in which the electrons are drifting inside the battery. The net flow of electrons is in this direction. When we discuss the chemical reactions that take place, this is indeed what's happening. So electrons inside the battery are moving from a positive plate to an already negative plate. So they are moving uphill. They are moving against the potential gradient. That's why the electric field is in the wrong direction, so-called. But where is that energy coming from? If you're moving against the direction of the electric field, then that energy must come from somewhere. That's coming from the chemical potentials at the electrodes inside a battery. Or if I use a mechanical analogy, I have a conveyor belt. That belt is just picking up an electron from a positive plate and shifting it to an already negative plate. But that belt is being manipulated by a pulley. That pulley is being operated by a motor. So there is an external energy that is being input into the system, which is transferring electrons against the potential. So inside, if you look at an electron, this electron is moving against the potential. So there must be some force acting on the electron. That's a non-conservative force. Some external source is supplying energy to move electrons uphill. Okay? So there must be some force that is acting on the electron. But there's an electric force acting on the electron, and it's in the opposite direction. If you look at this electron, the force on this electron is to the left. But the pulley is moving the electron to the right. So if I find out the net force on the electron, that is going to be Fnc minus EE. Okay? In other words, this is the net force on the electron. The electric field produces a force on the electron that is towards the left. The electric field produces a force on this electron towards the left, but this pulley is moving the electron towards the right. So the pulley is, so if I have this piece of chalk in my hand, gravity, the force of gravity is downwards, but I am lifting this chalk with a constant velocity. If I am lifting this chalk with a constant velocity, which that means that the force that I apply, which is a non-conservative force, the lift force has to be equal to the force of gravity if it's moving with uniform velocity. And this drift velocity is uniform, which means that this force that the pulley has to apply must equal this electric force. This equals 0, in other words. Which means that the force that the external agent has to provide equals EE. So how much energy does the external agent have to provide? Fnc, force times the distance delta S. Where delta S is the distance between the two terminals of the battery. This is the external energy that has to be supplied for a uniform drift velocity of electrons all around the circuit. This is the work that has to be done, come from somewhere. It can come from a motor, it can come from a chemical reaction, it can come from gravity, it can come from any source. It can come from a nuclear fuel cell. It can come from falling water in Mangla Dam. It can come from somewhere. This is the work that has to be supplied to make current go around so that the drift velocity is constant all around the circuit so that you have a steady current. Now this work done divided by the charge on a single electron is called the EMF of the battery. This is a physical description of what the EMF of a battery is. Units, joules per coulomb, which means the units are volts. Okay? Electric field, the dimensions are electric field into distance. Electric field into distance, this has units of volts, this is the potential. So what's happening around in this circuit is that around this circuit, if I were to draw how the potential changes around the circuit, path in the circuit, how the potential changes from, if I call this terminal of the battery F, if I call this G. At F, you start off at some potential, you drop down to 0 at G. So this distance is capital L. This is the entire length of this circuit. But inside the battery, this distance delta S is really small. So from L to delta S, the potential goes all the way back up. This point is called the EMF of the battery. The slope of this line is the electric field inside the battery. The electric field inside the battery has to be really, really large as compared to the electric field inside the wire, because this distance is smaller. So this is how the potential changes inside a closed circuit. Now what I would like to see is this situation here. You have an electric field and the line integral of that electric field is non-zero. So if this electric field exists, this has dimensions of EMF. But this EMF is not arising out of a separation of charges as they happen in a battery. It happens because of a changing magnetic field, and it's a non-conservative electric field. So even though this is not coming out of any battery or any charges, this has dimensions of voltage or EMF, and it's called the induced EMF. So the induced EMF E, right? A curly E is simply E NC, non-coulombic field, line integral over a closed path. This equals minus dV by dt of B dotted with dA, which is minus dV by dt of phi m. These are different variations of Faraday's law, one of 4 Maxwell's equations. Now, even though this electric field is non-conservative, but once it has been created, if there's path for current to flow and there are mobile charges available, current will flow. Because this is just acting like another EMF, although it's not due to charges, but it's just like an EMF. So if current can flow, it will flow. So if I have a situation like this in which there is a field that is pointing out, and that field is increasing with time, if outside this region I have a ring, a metallic ring, the field is pointing out and it's increasing with time. So I have the same situation as I've drawn over there. An electric field will be set up inside this ring, inside this metal. Okay? So inside the metal, electric field will be set up, it will be non-Coulombic field, and the direction of this field we've already drawn. If I draw it with continuous lines or field lines, it's going to point in this direction. Field is outward, dB over d out is positive and out and positive, which means that the EMF may produce a current that's inward, that will produce a field that's inward. That requires an electric field that's set up like this. Now this electric field is non-Coulombic. It's not due to charges. It's totally different from the mechanism of electric field formation in the case of a battery. The mechanism here is different. The mechanism here is from charges, real charges, Coulombic charges. Here the mechanism is different. It's a changing magnetic field that is producing an electric field. That electric field exists inside the conductor. That will create an EMF. That EMF can produce a current because the conductor has mobile charge carriers. That current is going to be E over the resistance of this medium, of this ring. So this EMF is produced from a non-conservative electric field, which is produced from a changing magnetic field. You don't really need batteries to make currents flow. You can have changing fields play the role of batteries. However, if this metal ring was placed outside, there could be an electric field set up in different regions, but then there will be no current that flows through the circuit because the EMF around this loop is going to be zero. Alright, now this non-conservative electric field can create a current. This is called an induced current or an eddy current. Eddy currents, the nomenclature eddy is generally used when you have unwanted currents or undesired currents. Sometimes you desire currents. So eddy is generally used in a negative connotation when something is undesired. Anyway, a non-conservative electric field is set up, its line integral is non-zero, it equals the rate of change of flux, the integral of this in this region. It can produce a current of its own. And of course you can find this non-conservative field from Faraday's law. ENC, if this radius is r into 2 pi r equals minus dV by dt of field into, if this radius is capital R into pi r squared, which means that the non-conservative field will be given by minus pi r squared over 2 pi small r dV by dt. This minus sign just tells us, is an indication of the direction of the non-Coulombic field that is produced. Now I would like to look at a few examples, a few applications in the last 10 minutes or so. So I've talked about how EC, the Coulombic field, is different from ENC. One is conservative, the other is non-conservative. I would now like to talk about some applications. The first example I would like to choose is a wire and a wire. Now an interesting example, right? It's a nice name. Okay, I have a wire that carries a current I. Now this current, of course, strong, long straight conductor, it produces a magnetic field. What's the direction of this magnetic field? It's going to be circular. Ampere's law will be provided, and it's going to point out here and in here. And it's going to be everywhere. Sorry. खामोश है दिल, बड़ी महफिल में चिल्लाना नहीं अच्छा. All right. So this is the direction of the magnetic field at some distance r. Let's call this distance r1. Then I can take any loop that I like. R2, right? So there's a field everywhere. बातें नहीं. क्या मुझे पूछो. There's a field everywhere and it's circular and it's given by Ampere's law. Now suppose that this current is non-constant. It's only passing through this conductor and this current is changing. And it's changing linearly. So with time, the current is going up. So it was at some steady state, and then it goes up. Okay, with a constant rate. That rate is di by dt. Now what I would like to do, I would like to place another wire close to this wire. And I would like to see whether an EMF is induced in that wire. Okay? And whether there is a nearby wire that I can place so that a current flows through that wire because of this changing current. So the configuration that I have here is the following. I have this original current carrying conductor whose current is going up, which means that these fields are going up with time. The magnitudes are going to go up, or even though the directions are not going to change. And I place a nearby conductor which is rectangular, no battery connected to it. And I would like to see whether current flows through this conductor or not. And I would like to invoke Faraday's law here. So this distance is R1, this distance is R2, and this length is, say, small l. If I would like to find out this path, let's call this circuit P. If I would like to find out E dot dl around P, which is just the EMF inside this wire, which will determine whether current is going to flow through this wire or not. Right? If I would like to find out E dotted with dl around the path P, which is just the EMF produced due to the changing current, due to the changing field inside this wire, I would need to use Faraday's law. Now, is there flux through this area? Yes, there is flux because there are field lines continuously coming out. What's the direction of the field lines? Outwards. So the field is coming out, right? Everywhere. And is this field going up with time or is it decreasing with time? Is increasing with time because the current through this wire is increasing with time. And is the field here the same as the field here? No, because the fields as a function of the distance from this wire are given by mu naught I over 2 pi small r. This is Gauss's law. Now the fields are coming out and they're non-uniform and they're increasing with time. So there is a changing flux through this loop, through the area bound by this loop. And that will give me the EMF. So I can calculate that. Minus dV by dt of B dotted with dA. Now this B is a function of R. and it varies from point to point. Now I would like to calculate the dot product of each B with a small area element. Now what would I like to do? I would like to break this area into small patches. And the patches that I would like to draw are, say if I redraw this, each patch I can draw a rectangular patch. Each patch has a length L and a width dr, and it's at a certain distance r from the current carrying factor. Okay, that will allow me to calculate this integral minus dv by dt. This b, now the area vector is pointing out, every local area vector is pointing out and the field is pointing out. So the angles are 0. So this will equal mu naught I, which is a function of time, by the way. Now this I has become a function of time. 2 pi r. This is a field at this point, at this rectangle. It's doing the same here as here, yes, here. Into dA. Now what's dA? Simply L dr. Now everything is a constant. This is with respect to r. And what are the limits of r? From r1 to r2. This will produce mu naught L 2 pi di by dt. The time derivative only applies to the current. Everything else is constant here. dr by r from r1 to r2. This gives me mu naught L over 2 pi di by dt, natural log of r2 over r1. So this is the net EMF that's produced inside this loop. And what will be the direction of the currents that are being produced inside this loop? They're going to go clockwise. The EMF that is going to induce will produce induced currents that go like this. Because these induced currents will create a field that's inwards, because the changing field is outwards. So there's a non-conservative electric field that's set up inside this conductor. Now the next lecture, which is tomorrow, I'm going to give you yet more examples of electromagnetic induction. Some really, really interesting examples. Tomorrow we're going to have a makeup class at 8 a.m. Alright? In 301, inshallah. Thanks a lot.